All right, so I want to figure out the velocity or the speed that this wiffle ball goes around the circular path, right? Okay. If you're taking notes, you still want to put this underneath Unit 4, and this I still put underneath Unit 4 UCM. What did UCM stand for again? Good job, Nikira. Uniform circular motion. Okay. So this wiffle ball is traveling around in a circle, so it has uniform circular motion. Right. So we're starting the equation. V equals change in position over change in time, right? Right? If I'm going around the circle, I said there was a C word that's going to help you. What's that C word again? Circumference. Sergio, do you remember the circumference equation?
Pi radius squared times. Yeah.
Sounds like a create your own ending story. Pi radius squared, something else?
Yeah.
I appreciate the effort, but I think you're thinking about area. Okay. Pi r squared is the area.
2 pi.
What is it?
2 pi.
2 pi r. Perfect. Thank you, Golas. So the circumference is 2 pi r.
Oh.
Right? 2 pi r. You could put pi r 2 or pi 2r. Okay? It's multiplication, it's commutative. It doesn't matter the order you do it. 2 times 3 is still 6. 3 times 2 is also 6, right? So if you did it in any order, Kevin, you're fine. Okay.
No,
Now,
I squared it.
Oh, you squared the p?
I had all the right things, but in the wrong formation.
Ah, that's all right. All right, so this wiffle ball is going around this circle, right? The 2 pi r. What is the 2 pi r? Where does that come in? Why is that important?
The radius is half.
Radius is half the diameter?
Oh, no, duck.
That is correct, but I don't think that's the reason why it's important. Okay. So as the wiffle ball goes around in the circle, right? It's traveling in one rotation. How far or how much of the circumference is the ball traveling? All of it, right? In one time around, the ball is traveling the whole circumference how many times? Once. So if we know how long it takes for the ball to go around the circle, right? And we know how long it is around the circle, then what can we figure out? No. The velocity. Good, because velocity is change in position or change in time, right? So the circumference is how far it is around the circle, right? If I were to break the circle at this point right here and stretch it all the way out, that would be the circumference, right? Right? So if I know the circumference, that's like knowing how far it goes in a certain amount of time. Does that make sense? So the circumference is what in this equation?
D.
Change in d, right? Change in position. So we know velocity is going to be 2 pi r over t. And that's the speed or velocity for an object traveling in a circle. Now, t, I'm going to change the t. I'm going to change it from a lowercase t to a capital T. The reason why I'm going to change this t from a lowercase t to a capital T.
Time travel.
Nope, it's not time traveling. You're hoping for that one, weren't you, Sergio? Okay. The reason I'm switching to a capital T, okay, is because the capital T stands for period. Okay. The period is the time it takes for one revolution. When I say a revolution, what does that mean?
One
Circle. One circle.
Good, one time around the circle, right? I'm glad no one brought up overthrowing the government. Get back to the conversation. Alright, so I'm glad no one brought up throwing over the government.
Good.
Alright, so the period is the time, usually in seconds, for one revolution. And one revolution is one time around the circle. It's really annoying when you open a parenthesis and you have to close it.
That's on the computer. We're trying to do codes and stuff.
Yeah.
Didn't put the other part.
Or when you're trying to correctly put in the quadratic formula.
Oh no, when you're trying to do coding for a game, you get one of those, you're in trouble.
Yeah. Alright, has anyone ever heard of RPMs?
What?
That's a form
In
of
the car.
speed.
RPM is not a form of speed.
Rolling. No, those are RPMs. No, never mind.
Okay. The tachometer in your car reads RPMs. It's usually in thousands.
Sorry.
What does RPM stand for? Close. Rate doesn't mean time.
Oh, word.
Revolutions per minute. Okay. So it's telling you how many times your engine fires in a minute. So when you have an RPM reading in your car of 2,000 RPMs, that means your engine is firing 2,000 times in a minute.
Is that good?
Okay. That means each piston is going to the end of its chamber, and then there's a reaction there with the gasoline that explodes the piston back out 2,000 times in a minute.
Is that good or bad?
That's a couple
So,
times.
that's good. That's fine. That's normal. Okay. When you start getting to like 4,000, 5,000 RPMs, if you have a stick shift, you better switch. You better change your gears. Okay. If you have an automatic and get to 4,000 RPMs, then you have a computer issue. You get checked out. Had that one time. It wasn't very fun. All right, but RPMs, like in the car world, stands for revolutions per minute. That's how many times it completes a cycle per minute. Okay. We work in revolutions per second. So the period is the number of revolutions per second. So it's kind of the same idea as RPMs. Right? Are there any questions about period or this equation? Any questions? Now, velocity is this way, right? Right? If I'm up here, which way is the velocity? Which way is the velocity? Okay. This way, right? If I'm over here, which way is the velocity? Down. Over here, which way is the velocity? The right. Because velocity is always perpendicular to what? What's velocity always perpendicular to? The circle. It's always tangent to the circle. It's always perpendicular to the... No! Radius! Thank you, Lynn. It's always perpendicular to the radius, right? Those always make a right angle. Okay? Now, which way is the acceleration at each of these locations? Which way is the acceleration here?
Down.
Down. You're thinking of gravity, aren't you? Yeah, you missed a good lecture yesterday. Ignoring gravity, I know it's difficult, but ignoring gravity, which way is the acceleration? Let's think about this. If I'm swinging this ball around in a circle, right? What's causing this ball to go around in a circle?
Your hand.
My hand doing what?
Moving it around in a circle.
Moving around in a circle. How do you know I'm moving around in a circle?
Because it's moving in a circle.
Okay, my hand's kind of moving in a circle too, right? But what is my hand doing to the string?
Pulling it.
I'm pulling on it, right? When the ball's over here, which way am I pulling the string? Pulling it that side of me, I'm pulling the string that way. When the ball's up here, which way am I pulling the string? Down. When the ball's over here, which way am I pulling the string? That way, right? When the ball's down here, which way am I pulling the string? Up, right? I'm applying what to the string?
Force.
A force, right? That's how I'm getting the ball to stay in a circle. If you don't believe me, I'll let you swing this ball later, okay? But make sure you don't hit somebody in the head with it, right? I'm getting really like I'm a teacher. You guys can't. ISS. All right. So if I swing this around, in order to keep in the circle, I have to keep pulling on the string, don't I? Right? Richard, when you swung the bucket around yesterday, did you have to pull on the bucket to keep going in the circle? Yes. Right? You had to pull on the bucket. I have to pull on the ball, right? If you don't believe me, let's give it a shot, right? But if I pull on the string, then I'm applying what was that F word again?
Force.
Force. Which way am I applying a force to the ball?
Whatever direction you're going. Yeah. Circulation.
All right, blue right here. So I'm applying a force in which direction?
Down.
That way, right? When it was up here, which way did I apply a force?
Down.
Down. When I'm over here, which way did I apply a force?
Right.
When I'm over here, which way did I apply a force?
Up.
Up. So what's the relationship between the force and the radius?
It's confusing.
Perpendicular.
No, it's not perpendicular.
You make a 90.
The force and the radius do not make a 90.
Oh, you said.
You're thinking velocity, I'm sorry. So here's the radius. What's the relationship between force and radius? Parallel. Good. They're in the same direction, aren't they? Right? Remember yesterday I introduced you to a new word called centripetal, right? What did I tell you centripetal meant? Center seeking. Force. Because they are seeking, they are pointing towards the center of the circle. They're pointing towards the center of the circle. Right. Those blue vectors are also what type of force? No, they're not gravity.
Oh wait. Kinetic.
Okay. String, right? Those blue vectors are also a tension. Okay. So centripetal force is not one type of force. Okay. It can be multiple force. It can be tension. It can be friction. It can be gravity. Okay. It can be electromagnetic force, and the force of attraction between electrons and protons, which is why chemistry is really just physics. All right. Special type of force. It's a bunch of different forces. It's whatever is acting in the situation. So in this situation, because the wiffle ball is being pulled with a string, that centripetal force is a tension. All right, and it's always towards the middle, towards the center. Good. So centripetal force is always towards the center. Now, does anybody remember?
Is that the one where
F net equals ma. Thank you, Moses. F net equals ma. Now, what do we know about F and A?
They'll always be the same,
Okay, they'll always be the same direction. Perfect, because M has no direction, right? M is a scalar. So F and A always point in the same direction, don't they? So which way is the acceleration of the wiffle ball at each of these spots? Which way is the acceleration of the wiffle ball at each of these spots? Same direction of the force, right? So here, which way is the acceleration? It might not be the same length, but I'm just drawing it so we can see it. Which way is the acceleration here? Down. The wiffle ball is a mass of 1 kilogram. They would be the same length. What about here? Right. What about here? Up.
That'd be a big wiffle ball.
That would be a big wiffle ball. So acceleration is in the same direction as the force. That's what Newton's second law tells us, right? So what do we call this acceleration then? It's towards the center, so it's called a good. Centrifugal? No. Centrifugal means center fleeing.
Center what?
Center fleeing. Means it runs away from the center.
I don't know that was an actual word.
Kind of like Valentine's dates and Sergio.
No.
No? Okay. So,
Did you hear, Mr. Grant? I'm actually singing for Valentine's Day. I'm not going to be here.
oh,
Sorry. Well, I'm saying
I won't miss you. All right. Centripetal acceleration.
No,
Which way is this point?
I'm very
Which way is this point? Towards the center. Okay. Now, there is a long geometric proof, which I'm not going to go through here. It's on page 153 and 154 of your book.
I don't even
That shows this next equation I'm going to put up here. Okay. It shows that the acceleration, centripetal, stop practicing. Okay. A sub c is always centripetal acceleration. Okay. The equation is A sub c, which is centripetal acceleration, equals v squared over r. Centripetal acceleration equals v squared over r. And if you're really interested in that proof, it's on page 153 and 154. I'm sure if you Google it, then you can find it as well. And I guess I shouldn't put this vector here. No, I should. I should put the vector here. There's a vector there. But v squared will always be what? V squared will always be, whatever you square number it is, positive. So since v squared will always be positive, this equation shows me that acceleration and radius are always in the same direction. Quick little thing I think we should point out before we move on. We know that velocity and acceleration are always perpendicular. And why do they have to be perpendicular? So it only does what, Lynn? Good. So since these are perpendicular, the acceleration only changes the direction of velocity, not the magnitude. Good, not the speed. right? So that means that this wiffle ball has a constant velocity as it goes around the circle, right? And that's because of this right here. Now from this, we also know that velocity is perpendicular to force and the radius, right? Because acceleration is parallel to force and the radius. I think I can write like this. You guys don't have unlimited space underneath your. You can write like I do. Right? So velocity is perpendicular to those three things always when we're going in uniform circular motion. Right? And that's because these three things are always parallel. Are there any questions? Are there any questions?
How did you spend your snow days?
How did I spend my snow days? Taking care of a sick child.
She's doing better?
Yep, my 2-year-old now has a cold. So she's doing better though.
That's good.